So now that we've understood mole to mole ratios a little bit more, now we're going to do full stoichiometry in mass calculations, because it's not always realistic to start with moles and be asked about moles. We know that we can convert from mass in grams to moles with molar mass as our unit factor. If we want to not just talk about one thing in a balanced chemical reaction, we want to slide across to some other species that's reacting or produced, then we need that mole to mole ratio that we just talked about. And again, practically, moles are kind of useless because we don't have a way of measuring them. And so a practical way of assessing quantities in chemistry would be to convert it back to the mass of our unknown, which again is molar mass and gives us back those useful units of grams. And so really what we're going to do is that mass to mole conversion that we were doing before, but now roll in this new mole to mole. So this is really chapter 8 with a little chapter 9 in the middle, and then back to the chapter 8 to answer the question. All of these assume that you're starting with a balanced chemical equation. The next example has a few things that are done for us just to kind of speed up the flow here. This is a question about magnesium hydroxide, or in an antacid of milk magnesia, and it can be used to reduce acidity in the stomach, or neutralize stomach acid, which is essentially hydrochloric acid, like this balanced chemical equation. So the chemical equation has been written for us. It has been balanced. The other cool thing is that all of the species, all of the things in the chemical equation have had their molar masses calculated. So I know you can do this, but I do find that those are kind of tedious to do. And so all that's happened here is that those have been calculated for you, right? You remember how to do that. And those are always in grams per mole, because that is our unit factor, that 1 mole equals however many grams. Okay, so in this case, again with them, I do find it handy to use that balanced chemical equation as a bit of a map, because in these you're often moving between one thing and another. And so this part says here, calculate the mass of magnesium hydroxide needed. So we want to know how much of this is needed if we have 5 grams of stomach acid. So you'll notice how this is different. 5.00 grams of stomach acid. Weren't given number of moles. That's how this recipe works. It's between the number of moles of these molecules. So we're going to always start with what we know, which is 5.00 grams of HCl. Number of grams is useless because these coefficients are in number of moles. And so we always want to convert to number of moles. And you convert to number of moles with the molar mass of the things that we were given here. So what this says is that 1 mole of HCl has a mass of 36.458 grams. So if we were to calculate this now, where we're at, and it's kind of handy to keep track of where you're at, you are now in moles of HCl. Now that has nothing to do with our final answer quite yet. So we're going to keep going on this, because now we don't want to talk about moles of HCl. We want to be talking about moles of magnesium hydroxide. Oops, that's an H. So those numbers out here in our mole to mole ratio come from our balanced chemical equation. So 1 in the magnesium hydroxide, I did a fancy one, I don't really know why, and a 2, in the HCl. We're going to keep going because it doesn't ask about how many moles of magnesium hydroxide are needed, but how many grams of magnesium hydroxide. So again, we're going to use the molar mass as the thing, I'll find the right one here, that goes between mass and number of moles. So we're going to be going away from the moles of magnesium hydroxide. You'll notice it's upside down this time, right? And we want to be going to the mass of the magnesium hydroxide. And again, if you want to go through and just double check your thinking here, everything should cancel out. So the moles of hydrochloric acid, then the moles of the magnesium hydroxide, we should be left, when I didn't do a complete unit here, in grams of magnesium hydroxide. So now everything's all laid out in a way that I can double check my thinking and give myself the time to do the math. I don't have to round in between, which would cause problems. I simply go across, and if something's on the top, I'm going to multiply by it. If it's on the bottom, I'm going to divide by it. So this in my calculator would be 5 divided by the 36.458 divided by the 2 and multiplied by the 58.326. I'm going to round all of this to the 3 sig figs from my original piece of information that was given. And on my calculator, I'm going to round that to 4.00 grams of magnesium hydroxide. All right, let's do another one. This one again is going to use the same chemical equation, but it's giving different pieces of information. So I'm just going to erase the information from that first question, and I'm going to switch so that we can see that I'm talking about a different question. We want to calculate the mass of magnesium chloride produced, so we want to know this in mass, so how many grams, when 25 grams of the hydrochloric acid is there to react. So again, this kind of maps it out. This is where we're starting. This is where we want to go. If we want to go between these, we can't go between masses. We have to go between moles. We need that mole to mole ratio. So always in these, you're going to start with what you know. So I'm going to start by writing out complete units. So 25.0 grams of hydrochloric acid, HCl. I'm going to convert to the number of moles of hydrochloric acid with the molar mass of hydrochloric acid, which is conveniently already calculated up here for me. Then if I want to go beyond here and get towards where I'm going, I have to do the slide between these two. I need the mole to mole ratio. I don't want to talk about moles of HCl. I want to talk about moles of magnesium chloride. Those numbers that go out front are from the balanced chemical equation. And then I can keep going because I don't have it where I want it. I don't want to talk about moles of magnesium chloride. I want to talk about mass of magnesium chloride. So going from moles to mass, again, I'm using the molar mass and conveniently calculated for me up here. Sometimes I get a little sloppy. I don't write everything everywhere, but when I don't, I tend to make a mistake. So in these ones, if you want to double check the pattern, grams of hydrochloric acid, moles of hydrochloric acid, moles of magnesium chloride, this is what our answer should be in. And if I've put the right numbers with the right units, everything should work out. So if it's on the top, multiply by. If it's on the bottom, divide. So punching all that into my calculator, and then rounding for the 3 sig figs that are in my original piece of information, I should get 32.6 grams of magnesium chloride. Give the one down below a bit of a work, because this time we want to know the mass of hydrochloric acid to produce 15 grams of water. And again, if you like using that balanced chemical equation as a bit of a map, go ahead and scribble that out. I'm always going to start with what I know. Grams are practical in the lab, but they're useless as far as chemical equations go. We need to convert things to number of moles. And going from mass to moles, we always use the molar mass, which again, conveniently pre-calculated for us. Sliding across with the mole to mole ratio, that's what allows us to transfer information from one thing in the chemical equation to where we want to go. And those numbers come from the balanced chemical equation. In this case, a 2 to 2 ratio, which is a 1, but you can just put it in your calculator if you're not sure. And then switching back to the mass of the thing that we're looking for with the molar mass, again, that is already pre-calculated for us. You can go through and see that zigzagging pattern. It's quite satisfying kind of to double check your work that way. Again, rounding to the 3 sig figs, you should end up with that as your answer. All right, so we're going to practice this with 2 more on the other page. This time you have a bit of space to work through. So this one is an unbalanced chemical reaction. We want to figure out the mass of each of the metals in the 2 equations on the page here if we produce 1.00 grams of the hydrogen. So that's what we're looking for to produce that. Now, if we want to make any sense of this, it has to be balanced. So I could start with the metals, move on to the hydrogen, and then finish up with the others. That should give me a balanced chemical equation. Again, if I've got nothing there, there is a 1 in front of those things. Okay, so I'm good to get going. I might need some molar masses of things, but rather than calculating all of them, I'll just calculate them when I need them. I'll give myself some space there. So I'm going to start with 1 gram of hydrogen gas. Grams of hydrogen aren't very useful, but moles of hydrogen are. So hydrogen gas, if I were to figure out the molar mass of it, it's 2 times 1.008 or 2.016 grams per mole as the molar mass. And that's what we're using as our unit factor here. If I want to slide across from moles of hydrogen to the moles of zinc, I need those numbers from the balanced chemical equation. Both of them are 1, but by showing this, it completes your thinking and it backs up any mistakes you might make. I want to finish this by figuring out what is the mass of the zinc. And so not the number of moles, but the mass, I now have to convert back to the moles of zinc. And luckily, it's just the element of zinc, so I don't have to do this funky business. I can just look it up off the periodic table. The molar mass of zinc is 65.38 grams per mole. And so now, again, you can analyze this. Oops, I made incomplete things in a few places. Calculate if it's on the top, multiply by, if it's on the bottom, divide. You can just ignore all the 1s because multiplying by 1 and dividing by 1 doesn't make a difference. Correcting to the 3 sig figs, I should get my answer of 32.4 grams of zinc. Last one to try. It's similar in that it's a reaction with a metal that it previously said we're going to have 1 gram of hydrogen produced. So how many grams of the aluminum are consumed in this? In order for us to make any sense of this, it has to be a balanced chemical equation. So that's something that's important for how this works. So starting with the metals, it's all good. Moving on to the hydrogens. It would be good to put a 2 there, but I do see that I've got this even odd issue with the chlorines. So if I double this up, I'm probably closer to making it work. So now I have 6 chlorines, so I need 6, and I can put a 3 here and a 2 here to balance that out. So again, we're starting with the 1 gram of hydrogen gas. You'd have to convert to number of moles of hydrogen gas, because that's how you can slide across in a balanced chemical equation. I've already figured out the molar mass of hydrogen gas. This is the act of sliding across. So what you don't want to talk about goes down below, and where you're going goes up the top. And those numbers have come from that balanced chemical equation. Almost there, because now I'm in moles of aluminum. If I were to do the calculations and stop there, I need to switch it back to the mass or the grams of aluminum. So off the periodic table, the molar mass of aluminum is 26.98 grams. And so I could double check all of my unit factors that it follows that zigzagging pattern of dimensional analysis, throw it in my calculator, round it to the 3 sig figs to figure out I'd be consuming 8.92 grams of aluminum if I had produced 1 gram of hydrogen.